how to balance our half equations. Remember that a half equation has got electrons in it, which is why it's called a half equation. You're showing where the electrons are, which helps you choose if it's oxidation or reduction, knowing that there needs to be another chemical for it to react with, or else it just sits there doing nothing, as it's only telling half the story. The reason I want to use permanganate is because it gives us a really good example for looking at different conditions, because different conditions lead to different products. This is why you need to learn that new table in your book, because there's a whole lot of new redox pairs that you need to know. One of the things that we need to know about a chemical like permanganate are the three possible products. One of them is Mn2+. It's pretty much colourless. And we should know that this has to be in acidic conditions. We don't get this product unless it's been acidified. So I'm just going to put in brackets there, H+. So we need to know how to do that balanced equation. This is the way that we learned to do balanced equations last year. Or half equations, I should say. Another possibility is that it goes brown. And that's often what happens when you don't put enough acid in it, or you forget to put the acid in it first. So that would suggest that this brown solid, this brown stuff, is actually when it's neutral conditions. Alright, because you forgot to put the acid in, it went brown, not colourless. That's a pretty common thing to happen. And the last one is pretty cool. It goes to this stuff here, MnO4 2-, which is green. And that only happens if you put lots of hydroxide ions there first. Okay, so I need to be able to write half equations for each of these. But first I need to know, by doing experiments, what happened. So, in one of our first reactions in our experiment, we saw permanganate being acidified, I would presume, with hydrogen peroxide. And it decolorized. There were some other observations which told us what happened to the peroxide as well, but it decolorized. So if there's no colour left over, then which of those species on the right in blue has been made? Mn2+. Awesome. I'm going to leave a bit of space here because balancing equations sometimes takes up no space, sometimes takes up heaps. So it goes to Mn2+. Okay, so for balancing this, first I check, are there the same number of manganese species, or manganese atoms, on each side? And there are. So that's cool. The next thing I look at is oxygen. Are there the same number of oxygens on each side? And there's not. There's 4 here and there's 0 here. So I want to add something into it. These were aqueous solutions dissolved in water. I want to add something that doesn't affect the reaction at all. It doesn't affect things. So what's something that would be in aqueous solutions that contains water, that contains oxygen and isn't going to affect anything? Water. Okay? So water has got oxygen in it, so I can use it to balance the oxygens on the other side. How many waters will I need? 4. The problem with that is I've now introduced another atom that isn't balanced. What's that? Hydrogen. Now, it says it's acidic conditions for this colourless one. So that tells me that I could balance those with the H+ ions. So how many H's have I got here? 8. So therefore I need 8 H+. That's the acidifying stuff. If I didn't do the acidifying, this reaction doesn't happen. That's why the H+, this normally sulfuric acid, is added in the first place. This is not complete. At the moment, if I do a bit of a balance sheet, on this side I've got 1 negative and 8 positives. So at this stage, this side adds up to a +7 charge. This side has a 2+ and no charge times 4, has a +2 charge. This is not balanced. What do I add to half equations to balance the charge, which is our last step? Electrons, cool. So I'm going to add, electrons have what charge? Negative. So I'm only able to reduce these two numbers. So I'm going to reduce this one until it gets down to -2. So how many electrons do I need to put in here? 5. Cool. And there is our half equation for permanganate under acidic conditions. The next one I'm going to do is under alkaline conditions, because it's the next easiest one. Okay? Sometimes balancing equations is really, really easy. Really easy. If I started with MnO4 minus, we then dissolved it in a lot of sodium hydroxide, and then added some iron 2 sulfate. Not much, just a little bit. And it went a nice green colour. Okay? Which one of those is green? Cool, MnO4 2 minus. Which is our green stuff. And that could only happen because we had lots and lots of hydroxide ions. If not, this would probably happen. Okay. If we have a look at this, are the manganeses balanced?
Yeah.
One on each side. Cool. What about oxygen? Yeah. So what's not balanced? The electrons. So this one's really easy to balance. Sometimes they are this easy. We just have to add one electron to get both sides to -2. -1 there, -1 there, -2 there. So sometimes they're that easy. You know I've left the middle one until last because it's not easy, don't you? Alright, so I'm just going to move that one up because I need a bit of space down here. The most common thing that we see in Year 12 experiments is this. It's gone brown. Why did it go brown? Did you add acid? Oh, no. Or, yeah, how much? Oh, a couple of drops? No, it's a couple of mils. So not enough acid being provided, which keeps it too neutral. So what we end up seeing is that MnO4 minus is turning into the brown stuff, MnO2. So it's going from manganese 7 to manganese 4. So it's still being reduced, but it's not giving us the thing we expected. Sometimes, though, this is exactly what we want to happen. We want to make the MnO2 as our product. So we start going through exactly the same process, but keeping in mind that if I have H pluses over here, it must be wrong. Why? Why can't I have H plus on this side?
Acidic.
Sorry?
Makes it acidic.
Makes it acidic, so that would actually happen instead. So you can't have H plus. What do you think you have to have on this side? I'll put it in brackets up there to give it away. H2O. You have to have water on this side. Okay? So this is a bit like simultaneous equations. You have to keep in mind that water, at the same time as this happening, water has the ability to dissociate into H plus and OH minus ions. Okay? So you just keep that in mind. I can cancel out hydrogen ions by having a certain number of this equation happening at the same time. Because it was neutral, so I can add as much water as I want to on this side. But I'm doing it to get rid of something that doesn't belong, H plus. Let's go through our process. Right, what was the first thing I did up here? Check what was balanced. Yep, that was right, even though it was muffled.
What? What was that?
The Mn, so the manganese, and it is balanced. Then I checked which element? Oxygen. Is oxygen balanced? No. 4 here, 2 here. So, what should I add over here, according to that rule? Water, okay? I'm getting it wrong to get it right. How many waters, though? Okay, so I need 2 of them. That then gives me hydrogens. How do I balance hydrogen? H plus, so I'm going to put some H pluses over here.
But that's wrong.
We know it's wrong, but we're going to get it wrong to get it right. So bear with us, it's a process. Then, what's the net charge on the left-hand side? +3. What's the net charge over here? 0. So how many electrons do I need on the left-hand side? 3. Okay. We know it's wrong because it's got these. We know it's wrong. But if I have a look at my equation below, this has got hydrogens in it over here, so they could actually cancel out. if I had how many of this bottom equation? 4. So if I have 4 H2Os, 4 H pluses and 4 OHs, that cancels out because they're on both sides of the arrow. What else is on both sides of the arrow? Water. So this one disappears and this becomes 2. Cool. So now I'm going to put all of that together and then double check that it is balanced. Okay? Just while I'm learning, I'll double check. So if I rewrite it, it becomes MnO4 minus plus 2H2O plus 3 electrons, MnO2 plus 4OH minus. What is the net charge on this side? -4. What's the net charge on this side? -4. That's your first giveaway, you've got it right. Let's double check the oxygens because that's pretty useful. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's good. And hydrogens, 2 waters gives us 4. 4 hydroxides gives us 4. So it's balanced it. So here's how you do it when it's not acidic conditions. You do it as if it was acidic conditions first. Find out how many hydrogens it puts in there, knowing that they don't belong. Cancel those hydrogens out by doing what's called the water displacement, water dissociation equation. This one here, which will cancel those out, and it will put water on the correct side and hydroxide on the correct side. Okay. By the way, looking at what is made here, if you kept reacting it, what colour do you think the permanganate will start turning next? Looking at what's being produced. Green. Very good. So it will actually get to a point where it's so alkaline, because the hydroxide's being made, that it will actually start making the green product instead. So it'll be brown, 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 then suddenly you'll start getting some green made as well. Alright. So using that case study, we've gone through 3 ways to balance equations. One is when it doesn't balance nicely under acidic conditions. One is when it doesn't balance nicely under alkaline or neutral conditions. And one where it balances nicely and all you need are electrons, so long as your atoms are all balanced. Any questions on those before I turn this off?